Hello, this is Dr. Baxley. This is part 4 of the Chapter 4 lecture video. In part 4, you're going to be learning about acids and bases, the pH scale, and some environmental chemistry. If you want extra reading material for this chapter, besides using the printable lecture notes, you should be looking at the two documents in Canvas called All You Need to Know About Acids and Bases and the pH scale. It'll give you a lot more information and some practice problems. First up are acids. Acids are substances that ionize to form H+ in solution. Now the H+ ion is often also written as H3O+, and it's called the hydronium ion. Acids typically react with hydroxide bases to make water and a salt. An example would be nitric acid, that in solution would react with a base like potassium hydroxide. If we think about net ionic equations, you would see that because nitric acid is a strong acid, it would be H+ and NO3-. Potassium hydroxide is soluble, so it would be K+ and OH-. And just with a double replacement reaction, the H+ ions would react with the OH- ions to form H2O. And the nitrate and the potassium ions would combine, and there would just simply be some potassium nitrate as the salt in the reaction. A salt is just any ionic compound formed from an acid-base reaction. Acids react with carbonates to make water, CO2, and a salt. And here's how that reaction would work. Another acid like acetic acid could react with a carbonate like sodium carbonate. Just like before, we can think of these as ionic substances. The H+ from the acetic acid could react with the carbonate. If we thought of it as a simple double replacement reaction, we would get H2CO3 for one product. The other product would be the salt, which would be the sodium acetate. However, this substance, H2CO3, otherwise known as carbonic acid, decomposes in water to make H2O plus CO2. CO2 is the gas. This reaction would have to be balanced, of course. There would need to be 2 sodium acetates to go along with the 2 sodiums in the sodium carbonate. And there would need to be a 2 in front of the acetic acid to make sure the reaction was balanced. It's really important that you know the strong acids and bases. There are 7 strong acid formulas and names you should know. Here they are. If you don't know their names, make sure you know them. Or another way to know what's a strong acid or a weak acid is to memorize all the weak acids. There are a lot of them. I'll let you decide which one you should memorize. Moving on to bases. Bases are substances that form hydroxide ions, or they react with acids. Some common bases you might come across in your daily life are sodium hydroxide, ammonia, NH3, which is used as a cleaner. Drano is typically a mixture of potassium hydroxide, maybe some sodium hydroxide, and sometimes there's some aluminum and bleach in it too. Milk of magnesia, or magnesium hydroxide, is another base you might come in contact with. You might have some in your medicine cabinet or find it in the pharmacy part of a supermarket. The soluble metal hydroxides are strong bases. So barium hydroxide would dissolve to make barium ions and hydroxide ions in water. You know all the other soluble bases like sodium hydroxide and potassium hydroxide and strontium hydroxide. Some molecules, like amines, are weak bases. They're kind of like weak acids in that they ionize in water to make ions, but they don't do it to a complete 100% reaction. So the weak bases ionize in water to make OH-. Here's an example. Ammonia is a weak base. ammonia will react with water and take one proton off of a water molecule, leaving OH minus behind, and the ammonium cation right there. But this reaction only goes to between 1 and 5%. So most of the substance in solution is the ammonia molecule itself. Here are some common amines that you might find in your day-to-day life. Pseudoephedrine is a common decongestant. Here is the nitrogen part of the amine, and it can form a reaction with an acid to be protonated, and then the whole substance would have a positive charge. Lots of medicines like sildenafil citrate are amines. This amine is possibly going to react with an acid to make a positive charge for that whole substance. If you're a horse person, you might give your horse glucosamine sulfate. Glucosamine has an amine, and it could also react with a proton to become positively charged. And then oxycodone, lots of synthetic opioids are amine bases, and so there's the nitrogen. It could react with a hydrogen, giving the whole substance a positive charge. You can see this list right here on the left side of the screen. Those are common anion names that you'll find that come along with amines. So check out your medicine cabinet. You might see some pseudoephedrine HCl, because the pseudoephedrine itself was reacted with HCl. Or you might find citrates, sulfates, tartrates, or nitrates as some of the anions that exist in common medicines. One might ask why the amines themselves are reacted with acids. One reason is that amines are often oily liquids. And no one really wants to take a medicine that's an oily, gooey liquid. But when the amine is reacted with an acid, like HCl or sulfuric acid, the protonated amine is now an ionic compound. And the ionic compound is much more likely to be a salt or a solid crystalline substance. It makes it a lot easier to make medicines out of. pH is a topic that's often discussed along with acids and bases. The pH of a solution is simply a measure of the acidity of the solution, or a measure of how many H+ ions are given in a particular volume of solution. pH is calculated by taking the base 10 log of the H+ concentration, or of the H3O+ concentration, and changing the sign. It's possible to back calculate the H+ or H3O+ concentration by raising 10 as a power of the pH, but to a negative value. Here are some examples. Go ahead and try this in your calculator and see if you get the correct answer. Simply by taking the negative log of the concentration of H+ in terms of moles per liter of the 0.000135, you would get 3.87. I urge students to use 2 decimal places for pH, kind of ignoring the significant figure rules. It's difficult to measure pH to a 3rd decimal place, or the thousandths place, and so 2 decimal places is usually sufficient. One can also calculate the H+ concentration from a given pH. Try this in your calculator, see if you get the right answer. By raising 10 as a power of negative 4.25, one can calculate the H+ concentration as 5.62 times 10 to the minus 5th molar. If you couldn't find the 10 to the x button on your calculator, it's usually right above the log button on your calculator. You just have to use the second function. At 25 degrees Celsius, there's a useful relationship between the pH of a solution, which we just discussed, and the pOH of a solution, where the pOH of a solution is just like pH, but this is the negative base 10 log of the OH minus concentration in moles per liter. So if one knows the pH value, one can calculate the pOH, or vice versa. For example, what's the pH if the OH minus concentration is already given? Try that in your calculator, see if you get the correct answer. Taking the negative log of the OH minus concentration, yields an answer of 2.90. The negative value is negative 2.90. The 2.90 can be subtracted from 14 to give 11.10 as the pH. The 2.90, of course, was the pOH. Here is a little chart for the pH scale on the far right side, the H plus concentration relating to that pH, and then some common substances that might have that pH. At the top of the scale, the red part is much more acidic, and then more basic is at the bottom, or less acidic. You can see some common items at the top of the list towards the higher pH values. Lots of food items are up here. It turns out lots of foods that we eat can be acidic, but if you notice, there's almost nothing that's edible here in the basic area. Most things that are basic taste really bitter. And that's not very pleasant for us. The term lime water might confuse people. That's not actual lime juice from a fruit. That's chemical lime, as in calcium oxide, not something you'd like to have. Lots of the basic materials, though, end up being cleaners, because cleaners tend to be basic in order to help dissolve fatty molecules. You might notice that natural rain has a pH here of about 5.5. Which is slightly acidic. Natural rain is slightly acidic because the water, as it falls through the sky, will interact with carbon dioxide in our atmosphere. And if we just add up all those elements together, you end up with H2CO3 that's dissolved in the water and lowers the pH a little bit, making it a little bit acidic. In our not too recent past, the pH of some rain has gotten all the way down near 2 or 2.5. Now that rain is very polluted rain, typically from burning coal to make sulfur dioxide, which then interacts with water to make sulfurous acid, and then it also makes sulfuric acid through some oxidation reactions that we'll talk about in the next video. No one really wants sulfuric acid in their raindrops, and no one really wants raindrops the pH of lemon juice or vinegar. Now water does something kind of funny to itself. Water will react with itself in liquid form and turn into the hydronium ion as well as some OH minus. If we look at the concentration of pure water, if we just started with the density of 1 gram per milliliter and worked to calculate how many moles of water are in a liter of water, it turns out to be about 55 moles per liter. However, in pure water at 25 Celsius, there's a very, very small amount of the H3O plus and a very, very small amount of the OH minus. This process is called autoionization. There's nothing we can do to speed it up or slow it down at a particular temperature. It just always happens. But if you look at the ratio of these two substances, 55 moles per liter of liquid molecular water and 1 times 10 to the minus 7 moles per liter of things that have ionized, it's clear that water can be treated like a molecule. There are very, very few ions. However, this shows us why the pH of pure water at 25 Celsius is equal to 7, because the negative log of 1 times 10 to the minus 7 is equal to 7. That's where the pH 7 comes from in terms of pure water. Now I mentioned acid rain briefly just a bit ago. Here's a castle in Westphalia, Germany. The original statue was created in 1702. The first picture on the left was taken in 1908. After 200 years of the statue being built, you can still see really interesting features. You can see folds on the dress, you can see fingers on the hand, you can see lots of facial features, you can even see some features of the hair on the statue. However, just 60 years later, you can see that the statue has been worn down. There are no more features of hair, hands, the dress features are largely gone, except in some areas. Over here it's still okay, but here where it's exposed to the elements of weather, you can see that much of the dress has been dissolved or removed. So, what causes all of this? Before the explanation, here's another castle figure. This one's in England, so it's not just a German problem. I'm guessing that whoever built this statue and created that face didn't know about this feature face. So I don't think he was trying to build Voldemort, but that's what it ends up looking like. Here's a map of the United States, and on this map are pHs of precipitation, snow or rain. You can see over on the west coast, most of the pH values are somewhere around 5.5. Again, that's fairly normal rain because of the lowering of the pH of pure water from carbon dioxide. However, if you start looking over on the east coast, you can see that the pH values are down more like 4, about a whole number lower than on the west coast. On the east coast, they burn a lot of coal. They use that as fuel for power plants to make electricity, and they use that in some industrial processes like for making steel. Now you might not think that a pH difference of 1 between 5.5 and 4.5 is a big deal, but remember the pH scale is a logarithmic scale. So the rain that falls in Pennsylvania and Ohio and parts of New York is actually 10 times more acidic than the rain that falls in California. That has a really big consequence in terms of things that react with acids. And you've seen some things in lab by this point in the course that react with acids, or at least you will soon in the chemical reactions lab. For example, metals react with acids, and carbonates react with acids. So acid rain is a big problem for things made of metal, like bridges and cars, and for things made of carbonates, like marble statues. So why does the pH of the rain get much lower in the East Coast and not on the West Coast? Well, part of that is the emission of sulfur dioxide. Sulfur dioxide largely comes from coal. Coal is a mixture of carbon, hydrogen, nitrogen, and a little bit of sulfur. When coal burns in air in a power plant, the products of the combustion are oxides of what's combusting. So CO2, which would contribute to global warming, H2O, nitrogen oxides like NO and NO2, and then sulfur dioxide. Sulfur dioxide is the molecule I mentioned earlier that reacts with water to turn into sulfurous acid and ultimately H2SO4, sulfuric acid. The nitrogen oxides aren't harmless either. They react with water to turn into nitric acid. Another strong acid, not much fun to have fall on you during a rainstorm. So, let's look at this little pie chart about Canada. In the year 2000, Canada belched out 2.4 million tons of SO2. Besides being highly polluting, they can't even spell tons right. Where did that SO2 come from? It came largely, 2/3, from industrial sources, making things in polluting factories, making things like nickel, chromium, and iron for steel. About a quarter of their SO2 came just from making electricity, so people could watch TV, watch videos, and charge their iPhones. About 2% comes from fuel combustion to warm houses. and about 4% comes for transportation, usually diesel fuel for trucks and trains. Let's see what the US is like. In about the same time period, 2002, the United States belched out 14.8 million tons of SO2. But at least we spell tons right. What do we do with that? Well, 2/3 for us is electric utilities. Not very useful considering Canada uses their SO2 budget to make metals for us. Only 9% of our SO2 budget is for industrial sources. We get almost 20% for fuel combustion, largely to heat homes. And then we have some transportation and other issues that produce SO2. It's not all doom and gloom though. Look at what's happened to the SO2 air quality from 1980 to 2016. On the y-axis is the concentration of sulfur dioxide in parts per billion. The national standard is the dotted line here in the middle. And you can see that the national trend from 1980 to 2016 is a really sharp decrease in the amount of sulfur dioxide that's in our air. It drops from a mean of about 150 parts per billion down to below 50 parts per billion in a mere 36 years. A remarkable achievement. Way to go, EPA. Again, not having the sulfur dioxide in our air prevents our air from turning into acid rain, drizzling down pH 4 or pH 3 rain, dissolving bridges, cars, and statues. Here's a little cartoon about how acid rain forms. The SO2 gets emitted from factories, power plants, or other places. The nitrogen oxides aren't harmless either. They mostly come from cars. As those pollutants go up into the atmosphere, they interact with water and oxygen and other substances and turn into acid rain that falls on mountains, cities, and farmland. Here's another cartoon. We've already covered the left half, where the pollution goes up into the air and turns into acid rain. The acid rain then falls down on farmland. The acid rain injures poor farm animals like baby cows and baby sheep. Maybe more importantly is that the acid rain causes nutrients like calcium, potassium, magnesium, and aluminum to be leached out of the soil, making it unavailable for crops, which lowers crop yields. Lower crop yields mean higher prices for food. Where do all those metals go once they leach out of the farm land? They go down into streams and rivers, polluting the streams and rivers. That causes loss of habitat and aquatic systems for snails and frogs and other creatures, of which fish rely upon. So yes, fish are damaged by acid rain. There are other acid precipitation events. If it's cold enough and high enough in the mountains, you can get acid snow. The acid snow damages spruce trees and maple trees. In the spring, when all the snow melts, all those acid particles rush down into streams and rivers, giving a big spike in the acidity or lowering of the pH. There's also some acid dust that will form, the stuff that doesn't rain out on us, and that can get sprinkled all over the place. Maybe you don't care about farm animals because you're a vegetarian. Maybe you don't care about crop prices because you eat cheap food. Maybe you don't like fish or frogs or snails. Maybe you don't like the snow or spruce trees. But most people are going to be concerned about this one item, the sugar maple trees that are imperiled by acid rain emissions or depositions. What's important about sugar maple trees? They make maple syrup. And wouldn't it be a sad world if we didn't have maple syrup? Here's a picture of the Sudbury smelter in Ontario, Canada. The smelter is 1,250 feet high. It's called the Super Stack. Now originally they didn't build the Super Stack at this smelter in Ohio or Ontario. Originally they started off with smaller smokestacks. But the smaller smokestacks would allow emissions to go up into the air and travel across the air and be deposited on some land nearby. The people nearby said, hey, there's a lot of acid emissions falling down on our cities and our land. It's causing us some problems. And so the good people at the Sudbury super smelter, they built taller stacks. So now the emissions would go further away. But those people finally noticed, and they said, hey, the next bigger stack could move those emissions even further away. And yes, you guessed it, someone said, hey. So now with this super stack, the emissions are high enough into the atmosphere that no one can trace them. No one can say, hey, Sudbury, you're causing our problems. Now you might think this is a Canadian problem. However, if you look to the west of us, way west, you can find a little country called China with about 1 billion people. They burn a lot of coal. They have super stacks that push their emissions up into the atmosphere. It goes through the prevailing winds to their east. It goes over the Pacific Ocean, and it lands in the Sierra Nevada mountains. Yes, we can detect now emissions from Chinese coal-fired power plants in the Sierra Nevadas. Here's a picture of my kids. They're in front of the Eiffel Tower in this picture. Guess which is taller, the Eiffel Tower or the Sudbury Superstack? You're right, it's the Sudbury Superstack by about 1,250 feet. Now, many people are interested in an idea called clean coal. What if we could just clean up the coal before we burn it, or maybe after we burn it, to prevent acid rain? Well, it's certainly possible. However, the clean coal muck has to go somewhere. It's kind of like cleaning up your closet. When you clean your closet, there's a pile of junk out in a dumpster somewhere that came from your closet. It's just like that with coal. The waste product from coal is called fly ash sludge. We make a lot of it in this country from our coal-fired power plants. You don't really need to know much about fly ash sludge to know it's bad, because it's got 3 really bad words in it. Flies, bad. Ash, bad. Sludge, bad. Fly ash sludge, triple bad. In 2008 in Tennessee, 1 billion gallons of this fly ash sludge spilled from a pond. The fly ash sludge contains a list of the world's worst elements, like mercury, arsenic, chromium, barium, cadmium. Throw in some uranium and thallium that are radioactive as well as toxic. You get a nice pot of muck from clean coal. This particular spill covered 275 acres, 6 feet deep. As I said, we make a lot of fly ash sludge, 131 million tons in our 460 coal-fired power plants. Here's an aerial image of the holding pond in Tennessee before the spill. Here's a color-enhanced picture of the holding pond after the spill. You can see all this area up here is where the fly ash sludge leaked into a river, where it then floated downstream until it was sort of corralled, scooped up into large barges, and shipped down to Arkansas. Now, this is not all doom and gloom there. A lot of great things have happened in our atmosphere in my lifetime. If you look at the left-hand graph, this is the air quality measured as nitrogen dioxide, sulfur dioxide, carbon monoxide, and lead for 28 years, 80 to 2008. The emissions index started at 100 in terms of how much stuff was in the air. By the year 2008, you can see lead is plummeted, largely due to the phase out of leaded gasoline. You can see that carbon monoxide has dropped precipitously, largely because of catalytic converters on cars. Sulfur dioxide has dropped dramatically, largely because of efforts to clean up coal and burn less coal. Nitrous dioxide, which really should be called nitrogen dioxide, little error from the EPA there, and nitrogen dioxide has also dropped by 50% over that time period. Another area of concern for air pollution is particulate matter, little pieces of dust that fly around in the air, so small that we can't even see it, but it gets in our lungs. This is for a fairly localized area Virginia, North Carolina, Tennessee, and Maryland, around where they have lots of coal-fired power plants. But you can see that starting in about 2007, there was a downward trend, a significant downward trend in the amount of particulate matter released into the atmosphere. Part of this was due to regulation, and part of this was due to the phase out of coal in preference of natural gas, which became much, much cheaper right about the time of the decline. We use far less coal now in 2016 and 17 than we did back in 2006 and 7, primarily because the price of natural gas being so much cheaper than electricity generated by coal. That's the end of the Chapter 4 video, Part 4, Acids and Bases. Again, make sure you go read that section on acids and bases. It'll tell you a bit more information about strong and weak acids, more than we did in this particular segment. There's also the one on pH with some practice problems.